So we started talking about conservation loss. Conservation loss is a special type of differential equation that we use a lot in modeling physical phenomena, which describes the quantities that actually conserve. And we derived three forms of conservation loss. The first form is called the integral form. The integral form of conservation law is directly derived from the physical concept of conservation. It draws in a control volume, so we call it omega, and tells you that the time derivative of the total stuff within the control volume, let's say the total stuff is U. U describes the density of stuff at a spatial location. So U is a function of space and time. This plus the flux through the boundary. So partial omega is the boundary. Okay. The integral of f, that is a flux function as a function of U, dot with the normal, ds. S is a small area around the control volume, is equal to an integral of omega a source term, which is also a function of U, ds. That's the integral form of the conservation law. From the integral form, which holds for any control volume, we can derive the conservative form. The conservative form takes the integral form and uses divergence theorem to convert the boundary integral into a volume integral. And by doing that, all the three terms in the conservation law becomes volume integrals. And the equation has to hold for any control volume. That means the integrand has to be equal on left and right hand side. And if you write that down, this becomes partial U, partial T at any spatial point. Plus now here the divergence of the flux at any spatial point has to equal to the source term. This has to be true at any spatial point. Now we get a differential equation. We also have the primitive form. The primitive form just takes the divergence of the flux and apply chain rule. You get partial U, partial T, plus df du, because f is a function of U. Df du is a vector field. This dot with the gradient of the conserved quantity is equal to S. That's the primitive form of the governing equation. And last time we used an example of the Burgers equation. The example of the Burgers equation is f of U is equal to what? U squared over 2. And also space is in one dimension. So the integral form I take as I is d dt integrated over spatial domain L and R times U dx plus what is now what in 1D, what is the boundary integral like? It's just 2 points. It's a summation of the integrand at these two boundary points, right? And what is the outward surface normal for this interval? N is equal to +1 at R, and N is equal to -1 at L, right? That's the normal, outward normal that points outwards. On left, it points outwards in the negative direction, so it's -1. Okay, so that means I have f of u times plus minus 1 at the two boundaries, which I write it down would be f of u at L and R, so at right minus at left. And let me just replace f of u by this u squared over 2 is equal to 0. Okay, Burger's equation s equal to 0. So that's the integral form. The conservative form, partial u, partial t plus the divergence in 1D, just the spatial derivative, partial x of u squared over 2 equal to 0. And the primitive form, partial u, partial t, apply chain rule to u squared over 2, we get u times partial u, partial x equal to 0. Okay, that's the example of conservation law as the Burger's equation, which is one of the simplest nonlinear conservation laws you can find, and that makes it very easy to analyze, and then the result of the analysis can be generalized to more complex equations. All right. So last time we took a look at the behavior of the Burger's equation. So we look at the behavior of the Burger's equation. Let's say if we draw more like a sinusoidal wave, right? So going from 0 to large and going back and negative. So we get both positive and negative solutions. And looking at how the solution would evolve. So you see that on the left-hand side, I'm drawing the solution as a function of time. And on the right-hand side, that's a space-time plot that we're going to use a lot in both demonstrating the numerical solution and also analyzing the behavior of the equation. We see time going in the vertical direction and space going in the horizontal direction. So what we see is that the behavior very similar to what we have in the behavior is very similar to what we have in the primitive form of the differential equation, right? So if you look at this equation, and the u is like the advection speed, we see that when the solution u is positive, the solution tends to propagate towards the right. When u is negative, the solution propagates to the left. And that makes the solution collide at a certain point, and the discontinuity would form. That's more like a shock wave. And the shock wave itself would move, in this case, slowly towards the left, right? A little bit. Right? Yeah. Do you have a question? No? Okay. So yeah, that's the solution of the Burger's equation. We see two very striking features that once we understand, we can basically predict the solution of the Burger's equation without solving it. These two features are these straight lines in regions where the solution is continuous, and the shock wave when the solution is discontinuous. So if we understand how the solutions behave in the continuous region, particularly what are the slope of the contours in the smooth region, okay? 1, and 2, the shock waves, how do they form, and after they form, in which direction and at what speed do they propagate? Then we can basically understand the solution of the Burger's equation almost analytically, right? And if we can generalize our analysis to a general conservation law, then we can use that analysis and intuition to predict the solution of general conservation laws. So this is what we are going to be doing this lecture. The first task is to analyze the continuous region of the solution. How do they behave? How does the color change? How does the solution evolve in the continuous regions? If you focus on the continuous region, what is the most striking feature do you see on this contour plot? The contour lines are straight. Very good point. So the contour lines are straight in space and time. That means the solution along these straight lines are constant. So how do you describe a constant in differential equations? How do you describe a constant in terms of differential operators? Zero derivative exactly along these lines. So you have all done project 1, right? You know, when you transform, if you take a spatial domain and transform it so that like the coordinates runs in diagonal or transform direction, and you take that spatial derivative or time derivative or whatever, and if you see the derivative to be 0, that means it is constant along that direction. So let's do analysis on that.